We stand on the threshold of a great new age of exploration. Its ultimate destination, the furthest reaches of the universe.
3, 2, 1.
Good evening, Raleigh-Durham, RTP, and everybody here. How's everybody doing tonight? That's good. You passed the first test. Welcome to RTP180 right here at Frontier on RTP and live streamed by our friends at PBS-NC. Give it up for PBS-NC back there, y'all. Excellent. We're going to have a great event here tonight talking about quantum computing. Now, some of you probably correctly are wondering why this weird bald guy is up here talking to you. Well, that's because I am your host for tonight's event. My name is Wade Mentor. I used to do this a long time ago, and I'm back for the first time. We'll see if I remember how to do it. But I was a previous host here at RTP180. They've graciously invited me back for this one. And for those of you who don't remember me, I am also the arena announcer for your National Hockey League Carolina Hurricanes. That's right. So now you know what I look like. You can't tell anybody. It's a secret. Also, we have great sponsors here, including our presenting sponsor, RTI International. That's right. Give it up for RTI International making this thing possible. And if you did not get one of their rechargeable fans out in the lobby, first of all, why not? Second of all, you can fix that. Go grab one of those at a convenient point in time. Now, as the great Humpty Hump once said, I've told you a little bit about myself. Now I'm going to tell you a little bit about this dance. What we're going to do here is we have 4 speakers, experts in the field of quantum computing. They're going to be up here talking to you, the audience, for 7 minutes. After that, we've got 7 minutes of Q&A from you, the audience, so be thinking of those questions. After that, we move on to our next speaker. Makes sense if you think about it. Also, if you are here, you probably don't need to follow along, but if you would like to socially mention us, you can follow us at the RTP. When you're on social media, you can use hashtag RTP180. And if you would like to see past RTP 180s, including potentially ones that have me in them, you can check out our YouTube channel. So we are everywhere there. Now, we're getting to the end, folks, I promise. We are here at the beautiful Frontier RTP, which is a home for creative freelancers, startups, STEM professionals, emerging companies since 2015. Yes. Yeah, thank you. Whoever did clap, thank you. In addition to free co-working every day, we host free weekly yoga, out-of-office happy hours, monthly lunch and learns. You see, I'm out of practice. I have to read this. And this quarterly speaker series, RTP 180. And right next door, you'll find Boxyard RTP, a hub for hyperlocal food experiences, weekly music, social events. The perfect spot for your working lunches and gatherings. Frontier and Boxyard are part of Hub RTP. That's right, the 100-acre downtown district of Research Triangle Park. Hub RTP has a lot more stuff on the way, including a lot of stuff that wasn't here when I was here last. We've got all sorts of cool stuff. Find out more about that by searching up Hub RTP. Now, as everyone is sitting there staring at me blankly, which is the correct response here. This isn't TV, you know. I can see all of you, right? You know that. Okay. Now, quantum computing, why are you here? Did you check out the stuff in the lobby? I hope so. If you checked out the stuff in the lobby, please raise your hand. Excellent. If you took time before the show to visit some of the information we have in the lobby, please raise your hand. That should be the same people. If you're somebody who never answers questions by raising your hand, raise your hand. That's called a paradox, and you just broke the universe. I'm sure we can get into that in your talk. Awesome. I have talked enough. You weren't here to hear me. You didn't even know I was going to be here. You are here for these experts. So introducing first, coming up to the stage right now, he's the director of the North Carolina State Quantum Initiative. Please welcome Greg Bird.
Hello, everybody. I'm leading off. I'm going to go to the next slide and say, this is what you should know about quantum computers. Now, I only have a few minutes, so I only can tell you some of what you should know about quantum computers. But let's get into it. Well, if you watch movies or TV, or you look on stock figures and you see you ask, what does a quantum computer look like? This is what you kind of see. You see this big, scary looking thing that's always, well lit in some spooky background, and it's always some powerful AI, all powerful thing, right? Well, that's not quite what they are, at least not yet. But I do want you to know that a quantum computer is not a bigger, faster computer, right? It's not the same as the computers we have now. And the reason we're talking about them is because they're different and they can do different things. So the basic idea of how they're different comes to this basic unit of information. So in our computers, we have a bit. A bit is either, as you probably know, 0 or 1. And that's how we represent information in our, what we now call, classical computers. A quantum bit, called a qubit, also has the 0 and 1 states, but the quantum state is a combination of 0 and 1. It's called a superposition of 0 and 1. So there's two different outcomes, 0 and 1, and it's got these numbers associated with each outcome that are related to the probability of observing that outcome. And so one qubit encapsulates two numbers, okay? Where a bit is one bit, a qubit is two numbers. And things get really interesting if we have two qubits, 4 different outcomes. Each one has this number associated, which again is related to the probability of seeing that outcome. And so we have 4. 2 qubits gives us 4 numbers. If I were to write down the state of this, I would have to write down at least 4 numbers. 3 qubits gives us 8 numbers. You probably know where this is going. 4 qubits, 16 numbers. 5 qubits, 32 numbers. It grows exponentially. So the amount of information we can encode in qubits doubles every time we add a new qubit. And so if we have this ability to create, manipulate, and observe qubits, we have this very large space of numbers that we can play with and search for solutions. Okay, so that's what really makes it quite different than classical computers. There is a catch, though. Remember, with my 5 qubits, I have 32 numbers, but I can't look at all of those 32 numbers in a quantum computer. If I ask the quantum computer, what is your state, one of those numbers comes out. Not one of those numbers, one of those outcomes comes out. And it's generally the most likely one, the one with the biggest number associated with it. But we get a classical piece of information out. So I've got these 32 floating point complex numbers, and I get a 5-bit number out, okay? And not only that, is when I do this act of asking it, what's your state, all the other numbers go away. It becomes that state and that state alone. So this is different behavior than what we have with classical computers. So the best things we can do with quantum computers, the best algorithms that we develop, are ones where we work alongside a classical computer. Quantum computers are not going to replace classical computers. They're going to work alongside them and do the things that quantum computers do best. And so we need to send in some information. All the information we have is classical, right? We send in bits to initialize this state. We send in bits that represent the evolution that we want these numbers to take, and all that happens, very efficiently and very, very fast in a quantum computer. And then we do this measurement, and we get a moderate amount of classical data out. So those are the kind of algorithms that we look at to exploit this power of quantum computing. Now, the other thing I want you to know about quantum computers is that there are several different technologies that people have developed and are developing that can implement this idea of a qubit. The one at the top, that's an IBM System 2. They use superconducting circuits to create this two-state system. It might be neutral atoms that we're going to hear about in the next talk. It might be ions. It might be photons. So all these different physical representations of the qubit, you'll hear about different kinds of quantum computers, and they have their pros and cons, and nobody really knows ultimately what the winner is going to be, right? What the most prevalent quantum computer is going to be, but everybody is making progress along these lines, and we will be using quantum computers in the near future, but we're still in early days. Right? Some people say it's sort of like where we were with computers in the 60s, perhaps. This picture's from the 40s, so maybe not that far back. But what I'm going to leave you with is these takeaway points. Number one, what I've talked about, quantum computers allow us to have this large solution space, but we only get a single answer, so we have to carefully craft our computation to take advantage of that. What I didn't talk about is that this quantum state that we create is very fragile, and over time it decoheres, it goes away. And so we can't do a lot just yet to manipulate our qubits, but something called quantum error correction is going to be the one that corrects this, allows us to run long things. As I've said, we're not going to replace classical computers. We're going to augment them. Progress is really happening fast. You'll see a lot in the press about things. And you don't need a PhD in quantum physics to use or program a quantum computer. And that's what I want you to know about quantum computers. Thank you very much.
Awesome. Good stuff. I remember playing Qubit in the arcades in the 80s. It was super fun. Orange guy, he jumped around. It was a delight. All right, excellent. Q&A time. So I've got my assistant Alicia back there. We'll start right here, and then Alicia, we can get that one over there. We'll start over here with you, sir. What is your question for Greg Bird about quantum computers?
Yeah, I'm wondering how well Bayesian neural networks could approximate the quantum superposition. So you essentially have a distribution of probabilities and kind of what the trade-offs are there.
Yeah, it's a little more nuanced than what you could do in a neural network. It's not just probabilities. We have this correlation between these states called entanglement. So there are aspects of this quantum state that aren't represented strictly by probabilistic computing. So it's more capable than probabilistic computing. So I know that people are trying to use AI to model some things that quantum computers can do, but I don't think it's something that they could actually mimic in a very substantial way.
Awesome. Thank you for the question. Alicia, who do we have over there?
Hey, Greg. Thanks for putting this together and sharing. Part of me wants to look at this as an evolution from 8-bit to 16-bit to 32-bit to 64-bit, but I don't really feel like that applies. What type of problems are quantum computers really good at solving?
I think that some of the later speakers are going to address this directly, but the ones that are most mentioned are simulating other quantum systems. So there's a quantum system that we want to understand. We model it using a quantum computer, and we learn things about it that way. Optimization is one, lots of possibilities in finding a solution quickly. There is a large activity in quantum machine learning. And then the one everybody's heard about is Shor's algorithm for factoring integers, which will change the way we do cryptography. So those are the ones that people sort of talk about as the closest. So chemistry, physics, problems like that are probably the most near-term applications.
It'll still never replace Excel. All right, other questions. We got one back here, sir. I will come back to you. What is your question on quantum computers?
Yes. For some years, I have wanted to see some quantum computer code, line by line, operation by operation. Where is a good place to get an introduction at that level?
IBM Quantum Learning.
Well, short and to the point.
It's all
All
written,
right.
It's all written in Python.
Ma'am, we will get you right here.
Just a quick question for you that work for IBM Quantum Innovation Center. What happened to the 7-qubit processor that was developed back in 2000? Do you know anything about it? You know, because there was an initiative from IBM back in 2000 where they used the 7-qubit processing computer, and I was just curious if you knew anything about that.
Well, back in that time, you know, 5 or 7 qubit machines were all that we could really build and control and be very precise with. Now, IBM has 150 qubits on a chip. They've built a chip that has 1,000 qubits, but their main thing is 150. So the state of the art now in terms of number of qubits, 100 to 150 is, and maybe 200, you know, are kind of where things are in terms of what people are building and able to reliably use these days.
All right, Alicia, I think we've got one over there.
Hi.
Hi.
First exposure to quantum computing, and the mind boggles from, and I'm not sure. But the question is, we are already facing challenges with like these huge data centers to process LLM and machine learning, but it sounds like these things can do a lot more processing with a lot less. So I'm curious to understand how that would have an impact on the power, the environmental, this land usage, et cetera, for data centers.
That's a really good question. First of all, these computers currently are very expensive, right? So that's one thing that I'm concerned about. They do require significant power. There's a lot of cooling. Some of these have to work at very low temperatures, and so you have to put a lot of power into the cooling. But I have seen some people believe that one of the early advantages of quantum computing would be to do something at a lower energy level than like a very large supercomputer or not. I'm not an expert in that, but that is one of the areas that that I've heard people say as a potential advantage.
All right, folks, give it up one more time for Greg Bird. All right, if you did not get your question answered, that's probably going to be a common problem tonight. But after this event, we will have a networking time, and some of our speakers may choose to stick around for that time. If they do, feel free to go up to them and ask them questions that you didn't get to ask on the microphone. But now it's time to move on to our second speaker of the evening. She's the assistant professor at Duke Quantum Center at Duke University and jointly appointed as the principal investigator at that center. Please welcome to the stage, Huan-Chin Lo.
Okay, thanks, Wade, and I'm really excited to be here. I work with neutral atom arrays in optical tweezers, and each bright dot that you see on the screen over here actually corresponds to a single atom that we can actually control pristinely in my lab. And so today I'm very excited to share with everyone the why, the how, and the what the what and the how you can use these neutron atom arrays for quantum computing. Okay, so like all the other platforms that are used for quantum computing and simulation, tweezer arrays need to be able to provide control of qubits that are scalable and programmable. Right, so by tweezer arrays, I mean arrays of single atoms that you can actually trap in these reconfigurable tweezers, and each tweezer holds a single atom, which corresponds to one physical qubit. How do I generate these tweezers? Well, I simply send laser beams through this microscope objective over here, which brings them to a highly focused tight spot. But now you might say, okay, if I want 100 qubits, doesn't that mean that I need 100 different laser beams? That doesn't sound very scalable at all. Well, it turns out that instead of building 100 separate lasers, you can use these magical devices, like this acousto-optic deflector over here, which basically takes one single powerful laser beam and splits it into many smaller laser beams, each of which can be individually controlled. So here you see a picture of atoms fluorescing inside 400 optical tweezer traps. But now, you have to know that the loading of single atoms into these optical tweezer traps are highly probabilistic. So just because we have 400 traps doesn't mean that we have 400 single atoms. And in fact, if you look at a single shot image of these atoms, it's actually full of defects. Now, is it bad to have defects? As alluded to just now in the question and answer session, one of the earliest applications of these noisy intermediate scale quantum devices that we have today is quantum simulation. And by quantum simulation, I mean that we tackle the kinds of problems that currently take up a lot of resources in a classical supercomputer, like materials research problems or chemistry problems. But now, we have these clever theorists, like the other speakers of the session, Lex, who write down equations that model these complex phenomena, and instead of feeding them into a classical supercomputer, we basically mimic those equations using the neutral atoms that we have in our lab. The underlying assumption, though, is that we need to be able to control these neutral atoms very pristinely, which also assumes that we start off with a defect-free array. But now you might say, wait a minute, you just said that the loading of single atoms into these optical tweezers is probabilistic. So if you want to have a large defect-free array, it's a very challenging problem. It's almost like saying that I want to have 100 coins, and I hope that I can get 100 hits. What are the odds? That's terrible. Now we can play some tricks instead. Suppose I don't have 100 coins, but I have 200 coins. And I flip them and I get roughly 100 hits. And I very quickly reshuffle them such that I have a defect-free array of 100 hits. Those are the tricks that we play over here with the second set of mobile optical tweezers that simply pick up those atoms and move them to the sites that we care about. So here you see actually successions of pairs of images, right? The first one is full of defects, and the second one quickly rearranges them. How quickly? Faster than a blink of an eye, about tens of milliseconds or so. In fact, there was actually this defect-free rearrangement technology that was invented in 2016 that really enabled the field of neutral atom arrays to take off in the last decade or so. And so here you see a few different images of programmable geometries that we can achieve, right? Like the honeycomb, which is interesting for understanding graphene, or the buckyball 3D figure over there. Now, so far, all of these atoms that you see over here are all non-interacting. Okay, so in order to get them to interact with each other, we need to drive them to these highly excited states called Rydberg states. This is also how we actually entangle different atoms together that we later use for this quantum computer. Okay, so far I've talked about using these neutral atom arrays for understanding materials, for chemistry, but there's actually one very exciting frontier that these Rydberg atom arrays are particularly good at tackling, which is solving optimization problems. Okay, so suppose you are the director of a mobile phone company, and you want to determine where to place your antennas such that you can maximize coverage of your antennas, but minimize interference between them. Where would you place these antennas? Well, if you've got many possible locations to choose from, the optimal choice of this antenna placement is actually a very challenging problem, right? It belongs to what we call an NP-complete problem, a non-deterministic polynomial time problem. Now, instead of solving this problem using brute force, turns out that Rydberg atom arrays actually offers a native hardware-efficient encoding of the solution to these kinds of problems. Loosely speaking, the idea is that we can actually arrange these atoms in arbitrary geometries to mimic the positions, the candidate positions that you have for these antennas. And then when we excite them to the Rydberg state, that strong interactions between them actually now mimics the minimization of interference between the atoms. And so solving these kinds of optimization problems have also other applications. For instance, figuring out how you might want to immunize a network against some virus that is spreading. Okay, so far what we've covered is all analog quantum computing, but if you want to build actually a more powerful universal digital quantum computer, which is what we are ultimately after, you need to be able to have entangling gates that are very, very good between two atoms. So here you can see that actually in the last decade or so, there's really been tremendous progress in this neutral atom array community, where in the last 5 years, for instance, you see the gate fidelity, the 2-qubit gate fidelity, go up by almost an order of magnitude. And impressively, the community has demonstrated that you can actually have these high-fidelity gates with between different pairs of qubits with up to 60 qubits in parallel. Remember those movable tweezers that you previously saw that we used to get this defect-free arrays? Now you see them again in a digital quantum processor, but they're actually used now to actually spread this entanglement through the entire array. So here you see, oops, okay. If you could play the video, please. Yeah, so here you see how you can use these movable tweezers to slide the atoms around and actually use this to generate the toric code, which is an important topological quantum error correcting code. And finally, you might envision what such a neutral atom array quantum processor might look like. You can have different zones, right? Some zones used for storage, others for entanglement, and some for readout. And again, you use these movable tweezers to come in and slide the atoms between the different zones. And it was just demonstrated last year, for instance, by a group at Harvard and MIT, that you can have up to 48 logical qubits based on about 300 physical qubits or so. Okay, so if there's only one message you could remember from this talk, it would be that neutral atom arrays are really a very fast-rising platform for quantum computing and simulation. The outlook is very bright. We have now demonstrated as a community up to 6,100 highly coherent qubits. There's also a big push towards making highly robust qubits, including here in North Carolina at the Duke Quantum Center. And there's really a lot of attention now from both academia and industry. That's all.
All right. I'm pretty sure atom-sized optical tweezers is how my grandma got her eyebrows to be just so thin. So thin. All right, if you have questions about what you've just seen, I have plenty of them, but I'm your host. Raise your hand. We'll come out there and allow you to ask them. Once again, Alicia, you found our first contestant.
Yes, thank you so much. That was very deep. What can you use it for? That's what I'm trying. What is the practical application for what you're talking about?
Right, so great question. The practical application for these optical tweezer arrays are basically using them to understand materials and chemistry. And one of the most difficult things about understanding materials, for instance, are their properties, right? If you can get a microscopic picture of what it really looks like in a material, you could use that to understand how to engineer materials that have better conductivity and other properties that you desire.
All right, we got a question right over here in the front row.
Is the tweezer process entirely manual, and or can that be automated?
That's all automated.
All right, other questions, other questions. We've got one here in the center aisle, so I'll come back here to you. All right, what's your question?
Thanks. So you showed something that looks very interesting, two-dimensional. Can you talk a bit about how you make it three-dimensional? Because two-dimensional, I think, cannot scale as well as three-dimensional.
Okay, so the question is about how you can make these tweezer arrays three-dimensional. So there are a few different ways to do them. That experiment that showed those images that had them, they actually used an electrically tunable lens, where basically you can use different voltages to tune the effective focus. That's one method.
All right, Alicia, who do we have over here?
Have you encountered a practical limit for the number of qubits you can implement this way?
Great question. So what limits the scalability of our platform? One of them is pretty much what is the field of view of the microscope objective that you're looking at, because you're limited in terms of, well, there's only so much space, and then you can only squeeze so many qubits in between with the tweezers. That's one of the limits. The others come in terms of the amount of laser power, right? I said that you could use these devices, but you must have a powerful laser to begin with to spread them out. Other things like the bandwidth of the devices and things like that.
Excellent. All right, we have a question here in the back. Find out some more information about potentially these tweezers. All right, sir.
My name is Pierre with IBM. Can you talk about how this architecture differs from IBM's approach using gates rather than neural atom array?
Right, so in the end, they are both quantum devices, both the IBM superconducting qubits and also the neutral atoms. They are very different in the sense that the neutral atoms that we get, it's not something that we actually have to fabricate. We just get them coming out of an oven. Every atom is essentially identical. And then in the IBM case, well, it's really very heroic efforts in terms of really trying to make them very pristine and things like that. Yeah.
All right, folks, give it up for Huan-Chen Lo. I really did hope one of our speakers was going to be talking about the movie Ant-Man and the Wasp: Quantumania. I don't think it's going to happen. Well, we still have two more chances, so bringing up to the stage right now, the Associate Dean of Research, College of Sciences, and Professor of Physics at North Carolina State University, Lex Kemper.
Okay, welcome to the quantum realm. So I'm going to tell you a story about simulating physics. So this was an old story. This is a series of questions written down in the 80s by a very famous physicist asking about simulating nature, in particular simulating physics, using computers. The first one is, can you simulate classical physics with a classical computer? So a classical computer is what you use today. These are your laptops, your desktops, your supercomputers. The answer is yes, we can. Here's a great example of this. Does anybody know what this is? This is the active part. Sorry? Not quite the three-body problem. This is, well, sort of. It's a space telescope that we launched 2 Christmases ago. We know very well where it's going to be. We can simulate plasmas, which I have on the top. We can simulate fluid dynamics. These are all very hard problems computationally, but we can do it. We can put them on a computer. So that's a thing that's certainly doable. How about quantum physics? Can we simulate this on a classical computer? Well, so this is also an old story. One of the oldest interesting quantum effects that you can find is magnetism. This wasn't really understood until the middle of last century, so this is relatively new. A great example is magnetite. The Greeks knew about this, and it took us several thousand years before we figured out what's going on with it. And we figured it out through really sort of a very simple model of taking little spins, ups and downs, and putting them on a lattice and looking at their statistical properties. And using this, we can explain how you get from a magnet to a non-magnet as you heat it up, and these sort of very fundamental physics things. So suppose I want to put this on a computer, and I would like to model this whole thing, right? Well, I have one spin that has 2 options, another one that has 2 options, another one that has 2 options, and I have to list all of those. If I have 50 spins, this is how many things I have to keep track of. It grows really quickly. Exponential grows incredibly quickly. And that's 50 of them, right? That takes 18 petabytes of memory. And I really want a mole of atoms. I want 10 to the 23 of them. I don't want 50. It's not enough, right? So you can kind of do this, sort of, but a lot of people work on this. My group certainly works on this. I work with experimentalists. We try and simulate quantum systems. We do so by making use of supercomputers. These are 2 examples of ones that I've worked on that sit either at Oak Ridge in Tennessee or at NERSC in California. And we do all sorts of simulations, but eventually they run out of something. They run out of memory. They run out of computer time. They run out of graduate student time. We always run out of something. So the hope is that to say, well, I have 50 spins, I should just use 50 qubits, right? That's the idea, because that's what we're supposed to do. And this is what Hongchen was also talking about, right? Simulating nature, things you find in nature, things that Greg also mentioned. Okay, so, and this is what the area of research is, right? So can we simulate physics using a quantum computer? There's some really great examples of being able to do this that have come out in the past 5 or 10 years or so. Still very limited to sort of simple things that we could have done otherwise and sort of proof of principle demonstrations. This is an example from one of the early IBM papers where they studied hydrogen, lithium hydride, and beryllium hydride, which are very sort of simple chemical molecules, but really the achievement here is the fact that you got an answer at all. You were able to simulate this quantum molecule on a different quantum system, which is really impressive. And so this is what we do. We build a new software stack. Instead of a classical one, we build a quantum one, right? And all the things that you do as a physicist or as a chemist, you take in all your input and you go and you calculate things. But instead of doing this on a classical computer, you do it on a quantum one. Okay, so yes, we can do this. We have a lot of work to do before this becomes really a tool that everybody can use and a tool that the community typically relies on. I'm going to add one more question. Can I solve classical computing problems using a quantum computer? This is sort of new. And really, if you go look at any sort of, I don't know, consulting company or whatever that's going to find out what is quantum computing good for, this is what you're going to find. All these sorts of interesting applications that have nothing to do with natural sciences, which is fine. Right? And so, where do you put radar towers or radio towers is one that was mentioned. Vehicle routing problems, all of these things have what I would call an unreasonably large solution space in that you simply cannot try all of them and check. Right? That's what NP-hard means. Turns out you can map them onto the same problem. So this whole problem of having a simple magnet that we'd like to try and understand, you can use that same idea to try and to solve these types of problems that are of interest to people that are not natural scientists, but that are trying to solve everyday problems. So then having that, we can now make use of all of our fancy quantum algorithms that people are developing, that they're working on very hard. And it's gotten to the point where people are actually showing some results. So this is a result from Los Alamos National Lab from a few years ago, where a quantum computer in certain situations, and they kind of cheated a little bit. They picked a problem that nicely maps onto the quantum computer, right? But it came to a better solution faster than some of the other competing techniques, and these are the kind that you would find used in industry today for complicated optimization problems. What else do we have? Greg mentioned Shor's algorithm. We have very efficient algorithms for certain things that we need to do. Right, so Shor's algorithm in particular is a great example of this. We can use quantum algorithms for integer factorization, and these days we can use them for, and that as a building block is usable for a very wide variety of other computational tasks you might want to do. Okay, so can classical computing problems be solved by quantum computer? The jury's out, but we have some nice progress in this direction. And things I have on the right is, well, I figured I should show you some data that comes from the quantum computer. So this is actual data. Some of it's from 2019, some of it's from last year. It's a little noisy, and we work hard to try and figure out what can you best do with this and how can you still make use of it. And that's what we work on. Okay, thank you for your time.
No Paul Rudd, sigh. All right, if you have questions about what you've just seen, I have plenty of them. But once again, I am the host. You are the audience. Raise your hand. We will come out there and let you get those answers to your questions. We'll start right here. Then, Alicia, we can get the gentleman with the glasses. As I talk to the gentleman with the glasses.
Hi, I come from software background. And my question is, would the programming interface for quantum computers or quantum computing would be different, like traditional programming languages and stuff?
Yes, so the question was, are programming languages different? Completely. You wouldn't even recognize them. They are more like reading a music score. As you are trying to keep track of what the qubits are doing, and you're telling them, rotate this way, spin this way, interact with another one. And so it's much more like getting a bunch of, like trying to get resonance to happen out of a bunch of classical oscillators. So it looks very, very different.
All right, question from the back there.
Hello. Thank you so much for this very in-depth presentation. Excuse a question from a red wristband. Application-wise, I heard years ago the application of your technology, quantum computing, would very much disrupt the internet security space because every password would be able to crack. Could you speak about that a little bit?
Yes, I will warn you, I'm not an expert on encryption. The point is that the sort of standard encryption that we use relies on not being able to factor very large numbers into primes. If we were to get a quantum computer that is good enough, it could do exactly that. And that would break the encryption schemes that are based on that. Luckily for all of us, we have post-quantum encryption schemes that we can immediately implement, and so that it will not be an issue in that particular way. But it's going to be a little while before the hardware gets to be able to do that.
Don't panic. All right, question from the front here.
So I'll be honest, I've been kind of struggling to follow anything that's been happening in the last couple of talks.
That's okay.
But what I'm understanding is with each qubit is that, to kind of put it in traditional computing language, is that just sort of exponentially more parallel processing with each thing, or am I kind of missing fundamentally what it's doing?
No, you're sort of right. It doubles your memory for every qubit that you add, and also enables more. Yeah, your algorithms can run faster as well. So I think you're correct.
Better than I could have put it. All right, question over here.
Hey, if you had a idea or something and you realized it most likely could only be solved by quantum computing, what would you recommend to someone facing that idea? Would you say, throw yourself at quantum computing or try to redefine the problem?
I would first make sure that you are correct and that the problem is actually only solvable by quantum computers, because quantum computers are great, but classical computers are all absolutely amazing too, and we make new algorithms. And actually one of the really cool things is that people are taking quantum-inspired things and bringing them back to the classical world and improving our algorithms there. But after that, yeah, go and learn.
Thanks.
Yeah.
As Blue Oyster Cult said, don't fear the quantum. All right. We'll go over here. We've been over this side before. Oh, it's you again. Well, I should have stayed over there. Anyway, what's your question?
Another quick question. Did you hear anything about like solving the Shor algorithm? Like if there is any update on that, like using quantum computing to solve that, the factorization of large numbers?
Yeah, the largest number I remember, and probably my other panelists will know better, but the largest number that I know we factored is 15. It's not very large. Am I off base on that one? Yeah, that's about right. So the problem is our qubits and our gates are not very good yet. Shor's algorithm needs a lot of them, and so that makes it hard to apply to actual problems you care about. And so this is also why, like you see, Greg mentioned early advantage we might find in simulating nature, simulating other quantum things, precisely because these other things require a lot more resources and our hardware is not good enough yet.
All right, got a question right up front here.
Okay, why do quantum computers make so many errors? And are we paying enough attention to error detection and correction?
Oh man, we have armies of people working on error correction and detection. The short answer of why they make so many errors is because qubits like to interact with the environment. And when they do that, they lose some of their quantumness. We can quantify what that means, but right? So you now have a problem. You need to isolate them really well, but you would also like to be able to interact with them at the same time. And those are completely the opposite direction, right? And so you try and find a sweet spot between these sorts of places.
Sounds like my teenagers. I'd like to isolate them, but interact with them every once in a while.
He's not wrong.
God, I wish I was joking. Okay. Thank you, and I'm sorry for laughing at that. All right, sir, what's your question?
Hi, Lex. I'd like to try a different take. Let me ask you, Lex, 25 years in the future, put on your crystal ball. How do you see quantum computing making our lives better?
So I've learned not to make predictions. So the goal that, let me do the following. The goal that I want is that I want a quantum computer to be a working tool for the researcher in physics and chemistry, natural sciences, and maybe optimization. I have less insight into whether that's feasible or not. I don't think it will replace everything. I think it's going to be useful for certain problems. It's going to be amazing for others. It's going to not be. But it's going to be, because it's now a tool that people use regularly, there will be areas of science that we can answer that we couldn't previously. So this might be areas of catalysis. This might be areas of non-corrosive coatings for airplanes. They might be, there's a whole wide variety of sort of like very specific questions that we have in chemistry and physics that are, if we can answer these using quantum computers, that's what's going to impact your life.
All right, give it up one more time for Lex Kemper. Y'all remember that show Quantum Leap? That's all I got. All right, please welcome our final speaker of the evening. She's the technical assistant to the VP of IBM Quantum with degrees from University of Pittsburgh and Duke. Our final speaker, Heather Saunders.
Thank you very much. Today, I want to talk to you about what's next with quantum. So what is, in the near term, quantum advantage? So I want to talk first about what is quantum advantage. How do we define that? And we define quantum advantage as performing an information processing task more efficiently, cost-effectively, or accurately using quantum computers than can be done with classical computers alone. And I want to point out especially classical computers alone. Like Greg mentioned, we don't expect quantum computers to replace classical computers. We actually expect they will augment the process. So we see that there will be heterogeneous compute resources, quantum and classical working together to outperform what we can do with just classical computers. And there's two parts to this advantage definition. First, we have to establish trust in the output. We've heard from the previous speakers, quantum computers right now are noisy. They make errors. So how can we actually trust that we're getting the right output? That's something that's going to be really important for us to be able to say, yes, there's a true advantage here. And secondly, quantum advantage is not something that we're just going to get. It's a milestone, and then it stays forever. As we've alluded to, this will be a back and forth situation, and a lot of times we've seen quantum advantage come out in something, and then we evolve our classical techniques using inspiration from those quantum techniques. So it's going to be a little bit of a back and forth where we say, hey, look, we found this better way to do this with quantum computers, and then people that are writing classical algorithms are going to say, oh, but wait, we can make our algorithm better, and so we actually can do it better. But honestly, everybody wins in that situation because we still get better computing, whether it's quantum or classical. Now I want to talk a little bit about when. We talked a lot about, yeah, it's going to take a while, but we feel pretty strongly at IBM that we are going to start to see credible quantum advantage by the end of next year. Now, this is not going to solve all of the world's problems. This is still going to be a research statement. This is going to be, we have advantages for using quantum computers with classical for those researchers to start solving those problems that they can't solve with classical alone. How? How do we think? How are we so confident that we're going to get this by the end of next year? So I want to talk about 3 different ways that we approach quantum advantage problems at IBM and where we see a lot of promise. Because remember, as I said, your computation is really only as accurate as you can trust that the output is. So the first method we use is methods that have provable confidence bounds, where you can say, I can statistically answer to you how much error there is and how much confidence I have in the answer that's coming out of this problem. And to do that, we look at things, to your question earlier, error mitigation, error correction, post-selection of circuits to say, we know these ones had errors, so we're not going to look at the outputs from those. And using error mitigation, we've been able to now run circuits that have 5,000 gates, which is not enough to do Shor's algorithm by any stretch of the imagination, but it's pretty impressive, and you can start to run some really interesting circuits. And if you look at this second graph there, that is a 50 by 100 entangled circuit. So a pretty complex entangled state that we're able to accurately simulate and get the answer that we're looking at. And all of this is underlying our technology to build fault-tolerant quantum computers, which will be able to detect and correct errors as they go, which will allow us to run much longer computational states. So the second way that we can have trust in the output is by using algorithmic approaches that have guaranteed error bounds. I saw variational algorithms in one of the other slides. So variational algorithms are a type of algorithm that takes a particular process and turns it into kind of an optimization problem. So we're optimizing, in this case, a ground state energy for a particular set of observables. And we know that it can't give us observables that are lower than could actually be possible. So because of the way the algorithm is designed, we know that if you get a lower answer, we know it to be correct. And in the graph that is on the right side of this, we're looking at experiments from an iron sulfide molecule that cannot be simulated exactly on a classical computer. And the lines, the horizontal lines, are showing you some of the most common state-of-the-art classical simulation methods. So DMRG, way down at the bottom, is the best known but somewhat inefficient classical method for simulating these ground state molecules. CISD and CCSD are much more efficient algorithms, and you can see the data that's coming out of our quantum computer is in line with those efficient classical solutions. And this gives us confidence that this is a really interesting problem set to work on, because even with today's noisy quantum computers, we are already getting answers in line with what we know to be true on the classical computing side. The last is problems that have efficient classical verification. So these are problems where it might be really hard to get the answer, but once you get the answer, you know it's true, or you at least know it is a verifiable answer. So this is where you start to run into those optimization problems that we've heard a lot about. The first one is a little bit of it's a little made up from a quantum perspective, but it's sort of exploring different things that we can do with quantum, where you give a very difficult to run circuit that has a high probability of giving you a particular output. So we call that a peaked circuit. So one of those outputs is very common, like it has a 99% probability if you create the circuit correctly. Now we can verify that very easily because we know what that number should be, but it's very difficult to either create the state and very difficult to simulate classically. So there's a company called Blue Qubit that has a challenge out there for a number of these peaked circuits running both classically and with quantum. And then we also look at optimization problems. Again, we can verify that you have a good answer to an optimization problem by checking it against our parameters and making sure those parameters are in bounds. Do we know it's the absolute best answer? Maybe not, but we know it's a verifiable answer. And so we have a working group at IBM between a number of different, that we started, but has now sort of evolved into a number of different industries that is looking at optimization problems, and they've come up with what they call the intractable decathlon of difficult optimization problems they think might have traction with quantum computing. So lastly, I just want to leave you with this. We think quantum advantage is not very far away, but it is really just the first step. Quantum advantage, we will start to be able to use these as research tools, and the next step is how do we take those research tools and discover a whole wide world of new things with those techniques. Thank you.
Quantum Advantage, the new card from Capital One. All right. If you want to learn about what the future may look like, the very near future, here's a chance to raise your hand. We have got one all the way in the back here. I'm coming, I got little legs. All right, what is your question about the quantum advantage?
Okay, oh, can you hear me? Okay, so I'm not very sure of this question, but after achieving quantum advantage, or even if quantum advantage is necessary, how long do you think it'll take for us to actually start designing products that are based on quantum abilities? And like, what are some obstacles do you think that need to be overcome in order to get to that point?
You're asking me to put on my crystal ball now. No, it's a great question, because as I said, what we define as quantum advantage really is a scientific advantage, right? And so that is, can we get quantum computers in the hands of researchers that are going to be the best tools for the problems they're trying to solve? And so it's difficult to then say, how long is it going to take them to take that tool and turn it into something that is really applicable. But we already now today are working with a number of different industries at IBM to look at what those use cases are and start to develop those algorithms so that they can hit the ground running. So it's not going to be, end of next year, like quantum advantage, I think. But we are fairly confident that we will be able to put out the first of those fault-tolerant quantum computers by 2029, and in 2033 have a much larger version of that we believe actually has, it actually has algorithms that are at the scale that could be run on that 2033 computer that could be useful for that kind of development. So,
Alicia, we got somebody over here.
Hi, thank you for your presentation, very interesting. I'm gonna try to make sense of this question, okay? It makes sense here already. I'm a linguist, I'm a translator, and I've been taking a lot of advantage of large language models, generative AI, and I'm here because I'm trying to see how can I take advantage of this, of quantum computing. Before getting there, I have a question regarding, is there anything, because I don't think I have heard thus far mentioned the combination of, like, you are working with quantum computers, there's a lot of noise there. Is there a way of, are you working with denoising those results using generative AI? Is there any link there to feed that information to large language models?
So we do have a couple of groups at IBM that are looking at both using AI for quantum, for improving the way that we run algorithms on quantum computers, for example, and certain assistive techniques for things like error mitigation, but also things for compiling circuits, making quantum computers run more efficiently. And then on the flip side of coin, there is also a lot of active research on can we utilize quantum computers to improve AI training, AI modeling, things like that. So I think the intersection of quantum and AI is definitely a very active area of research from both directions.
All right, question up front.
Maybe a basic question. You and some of the other both talked about logical qubits and physical qubits. Could you explain the difference and why that matters?
Yes. So a physical qubit is just that. You could take one atom of a neutral atom array or one superconducting qubit. That is a physical qubit that you can create a quantum state on and then observe. A logical qubit is a qubit, kind of a virtual qubit that is made up of many physical qubits interacting, and that is one way to approach, or really the foundation to approach from an error correction standpoint. So you're using the states of many physical qubits plus mathematical error correcting codes to give you that virtual qubit that has a lower error rate.
All right, see if we can get a couple more questions in here, sir.
Thanks, Heather. It looks like a lot of this applies to molecular simulation. Does it also apply to sort of drug discovery and interaction, or is that too far out there?
No, absolutely not. IBM has installed a quantum computer at Cleveland Clinic in Ohio, and there's a lot of active research in the molecular interaction space. So they've looked at molecule-solvent interactions as well as some intermolecular interactions, and I think they are definitely looking at medicinal properties. We've also worked with Moderna to look at things like RNA, how RNA sort of self-assembles itself into different shapes, things like that. So definitely within that realm.
All right, question from the center aisle here.
Hey, so I liked your presentation. I'm a high schooler and it was really easy to understand. So I know you talked about how quantum advantage can be more useful and effective for solving problems, but do you think that it would make a bigger difference in solving types of problems that we're already familiar with, or would it make a bigger impact in solving new questions that we haven't tackled yet?
This is a personal opinion. I'm more excited for what we don't know. So I'm more excited to know what are the problems that we have no idea how to solve today, and that somebody who right now is maybe sitting in a lab thinking about that's going to come out with this new way once we get these new tools into the hands of scientists, because quantum computing runs on fundamentally different math. And so there are fundamentally different techniques and problems that you can now use to solve problems. So I personally think that that's going to be the much more impactful space.
All right, give it up for Heather Saunders. Folks, this has been RTP180 for August, Quantum Computing. One more time, give it up for our speakers, Greg Bird, Hwan-Chin Lo, Lex Kemper, and Heather Saunders. Now, before we open up the bar, wait for it, you degenerates. We've got a couple more things to talk about. First off, there will be the networking time after this. Some of our speakers may or may not stick around. If you see them and you have other questions, feel free to approach them. Don't be scary. They won't be scary to you. Second of all, we've got another RTP 180 coming up, and that's going to be in November. It's a topic that's very near and dear to my heart, nose, and lungs at least half the year. It's allergies and allergens. Yeah, you can come find out what to do about those. Once again, registration opens on October 20th. RTP 180 for November will be on November 20th. On behalf of our friends at PBS-NC, on behalf of our presenting sponsor, RTI International, and all of y'all here, I've been your host, Wade Minter, saying thanks for coming out and have a safe journey home. Good night, everybody.